Hello everyone, welcome back. If you are new, this is a new series that we have started in which we are trying to dissect segment trees from scratch. We already have 6 videos in this series in which we have discussed how to build segment trees, how to do point updates, range queries, the detailed complexity analysis of each of these methods, and the entire code walkthrough. After that, we have gone ahead and tried solving a special variety of problem wherein we are asked to query on the prefix of an array. We have solved various different problems of different difficulty levels in this category. And finally, in the last video, we started with how to do binary search on a segment tree. So there is already a sheet bit.ly slash segment trees, which we are trying to maintain, in which I have pasted various different problems, which you can try out yourself after watching each of the videos there. And we also have solutions for many of the problems here. So if you haven't watched any of them, strongly recommend to check them out. In this particular video, we would be continuing with this binary search, which we have introduced in the last video. In particular, we will be solving one problem on this binary search and see how it is implemented as well. So with that, let's start with the brief recap of the previous problem which discussed in the previous video. The problem was we are given an array and we need to answer some queries. The queries are of two types. First query says that give me the index or the first index where the prefix sum becomes greater than equals to x. For example, if let's say the value of x is equals to 6, so you will say give me the first index where the prefix sum is greater than equals to 6, and the answer for that would be 2 because this is the first index where the prefix sum is greater than equals to 6. You can see if you take 1 and 4, the prefix sum is still 5. So this is the first index where prefix sum becomes 7, which is greater than equals to 6, and hence the answer is 2. So this is the first query. Second query is update the value of ith index to x, right? So as you might already have noticed that the first query is can be simply solved by doing a binary search over the prefix sum array. But because of second query, we that approach would not scale because if you let's say update the value of this particular index to 3, the prefix sum of this entire thing of it will change, right? This will become 8, this will become 9, and this will become 11, and so on and so forth. So this was the initial approach where we just use prefix sum, but as we discussed, this will not scale because of second query. So we saw that prefix sum is nothing but a sum of integers in the range 0 to m, right? So what we have a point update and a range query. So we just thought of segment trees and we introduced a segment tree where each of these elements in the array represents uh, the leaf nodes, and we build a segment tree over sum. And this query can is trivial in segment tree, and for answering the first query we still have this binary search. The only thing that changes, instead of using that static array, we now query the segment tree for getting the prefix sum of 0 to m, right? So this entire solution works in order q log square n. Then we gone ahead and tried to optimize this further to q log n. And how we done that is we noticed that this the ranges in segment trees progresses in a very similar fashion as in binary search. For example, in binary search, what you will do, you will first try to split the range into half. So it will be 0 to 3 and 4 to 7. Now you will either go in the left half or in the right half, right? So if you go in the left half, you will be searching in the range 0 to 3. Similarly, if you are searching in range 0 to 3, you will divide into two parts. So the left part would be the range 0 to 1, right part would be range 2 to 3. So you will either go to the left or go to the right, right? So you can see the left half of the segment tree exactly denotes 0 to 1 and the right half denotes 2 to 3. So basically how binary search propagates, in the similar fashion our ranges in the segment trees are propagating. So we can directly use segment trees to do the binary search. How? So let's say the value of x is 6. So this is like the exact same array 1421230 which we had here. Now we have to solve these two queries. Let's say we are solving the first kind of query, because second kind of query is trivial in segment trees. We have discussed this many times in the past. So to answer the first one, we have to, let's see what we have to do in this segment tree. So if x is 6, we'll just say, okay, divide into half. The left half sum is 8, and 8 is greater than 6. It means we will have the answer in the left half itself. So we'll go to the left from this particular root node. Now from here again we'll do the same thing. We'll divide into half. So what we will say is, okay, find me the sum in the range 0 to 1, or find me the sum of the left half. You will get 5. Now 5 is actually less than 6. It means what you are finding will not be in the left half. Instead, that will be in the right half. Now notice that the right half only contains everything in the range 2 to 3. So you will not get any contribution of the 0th element or the first element if you go to the right. So therefore what we said is, okay, we'll just subtract the contribution of the left half before going into the right half. So now once we go to the right half, instead of searching 6, we will be searching everything 6 minus the contribution of the left half, which is 5. So we'll be searching 1. So at 3, we will be saying that, okay, what is the left one? Left one is 2. So we'll compare 2 with 1 instead of comparing 2 with 6, right? So as and when you reach a leaf node, that will be your answer. So the complexity of this entire thing is log n, because we are just traversing, we are going either left or the right, and we are ending our journey at the leaf node. So this approach brings down the complexity from order q log square n to order q log n. Now again, this was just a quick walkthrough. If you have any doubts in any of the three solutions that we have discussed, I would encourage you to check the previous video out. I would link that somewhere in the top right hand section or description down below. So let's start with the problem that we want to solve in this particular video. That is a problem of the lead code, which is sliding subarray beauty. So the problem can be solved without segment tree as well, because the constraints are pretty low here. But irrespective, we will be trying to solve the same in an efficient manner using segment trees. So let's see what the problem statement says. You are given an integer array nums. You have to find the beauty of each subarray of size k. Now the beauty of a subarray is the xth smallest integer if it is negative, or 0 if there are fewer than x negative integers, right? So in finally you have to return a subarray of size n minus k plus 1, because there will be total this many number of subarrays of size k. So let's take an example. Let's say this is the array, k is 3, x is 2. So you want to find the beauty of each subarray of size 3. So let's take the first subarray of size 3. In this case, the beauty would be the xth smallest integer. In other words, the beauty would be the second smallest integer. Second smallest integer is minus 1, right? So minus 1 is the second smallest integer, and hence the beauty of this particular subarray is minus 1, and hence the first element in the answer is minus 1. Now the second subarray of size k is this. Again, if you find the beauty or the second largest or second smallest element, you will be getting minus 2, and hence the second element minus 2. And finally, you will see the third subarray of size k, and the beauty of this subarray is also minus 2, and hence the third element in the answer is also minus 2. So this was the problem statement. We, like, I already have created a detailed video explaining how to approach this particular problem step by step and reach at a particular solution. So if you haven't watched this video yet, or you don't know how to solve this, I would strongly encourage you to watch this one first before moving ahead in this particular video. So just to do a quick recap, this was the solution that we have discussed or reached at in the previous video. The, let's say k is 4 and x is 2, and this is a subarray. This is an array of size 8. Now we have to find the beauty of every subarray of size 4. So what we have said is, we will just go ahead and maintain a frequency array for the elements that we have seen in the current subarray. So in the current subarray, we have seen that 1 occurs 1, so we'll increment its frequency to 1. Minus 1 occurs 1, so we'll increment its frequency. Minus 3 occurs once, so we'll increment it frequency. And 2 occurs once, so we'll increment this frequency. Now, to get the xth smallest element, what we need is we need to just find out the first index where the prefix sum is greater than equals to 2. And that would be the xth smallest element, or that would be the beauty of this particular subarray of size k. So isn't this problem finding the first element that where the sum is less or sum is greater than equals to k or x is equals to what we have seen before? Uh, the answer is yes, right? This is exactly the same problem that we have seen before, and hence you might imagine already that this can be solved using segment trees efficiently as well. So let's just move forward before, once. So let's say you now consider the second subarray. So in second subarray, what we have seen is we have removed this particular element and we have added this particular element, right? So what we will do, we will remove the contribution of this element. So we'll remove the contribution of 1 here, and we will add minus 2 contribution. In other words, we will say minus 2 occurs once, right? Now again, to find out the smallest element, we will just find out the first index where the prefix sum becomes greater than equals to 2, and in this particular case it would be minus 2, and hence the answer would be minus 2, right? So we'll keep on doing this, and we'll finally get the final array of size n minus k plus 1, which denotes the beauty of every subarray of size k, right? And this is how the pseudocode would look like for this particular solution. So we'll first add every element up till k minus 2. So if you notice here, the first range is this, right? And then the second range is this. So for the first range, what we are doing is we are first adding everything up till first k minus 2, right? Now once we have done this, after this what we have to do, we just need to add the last element and remove the previous element. That's what we have to do, right? So that's what we are doing. We are first adding the last element, getting the answer, and then removing the first element, right? So we add the last element, get the answer, and then we'll remove the contribution of this particular element. And once we get to the next one, we'll again add the contribution of this particular element, right? So the xth largest currently is implemented using an order n algorithm, but as we have already seen that this can be implemented in order log n very easily by using segment trees. So if you have watched till this point, I would strongly encourage you to pause the video right away and try to code this particular solution yourself and get it accepted in LeetCode as well, because as we have discussed, this solution will just be a optimization to the brute force solution, and the same you can use the same test cases to verify your correctness of the solution. So finally, let's look at the code. The code is the main function is exactly similar to what we had before. We'll just add everything up till k minus 2, and then we'll add the nums at j, or the last element here, find the answer, and then remove the first element, right? So previously, add function was just adding to this frequency table, or just doing like frequency 2 plus plus or frequency minus 1 plus plus. Now it's a point update to the segment tree. In other words, what we are saying is we want to update a particular index or increment a particular index value by 1. Now this is the index, like we got a value, right? We got 1 from here, but if you look at it, we need to increment the index 4 in the array, right? So that's what we have done. We have simply created two mapper function which will map from index to value and from value to index. So we call this value to index function and get a particular index which we need to update in the segment tree. And finally we add plus 1 to that particular index. Similarly, for remove, we get the particular index and add minus 1 to that particular index. Now, finally, xth largest, we just have a new function in the segment tree which says first index greater than prefix sum x, and we are passing in the value of x. So we look at how this is implemented. Now finally, once we get the particular index, we have to return value, right? So we figure out what the value is with the reverse function tree index to value, and if the value is greater than equals to 0, we return 0, otherwise we return val. So now this condition is just because the problem says that we need to return the xth smallest integer only when if it is negative, otherwise you have to return 0. So that's what we are doing. If xth smallest integer is greater than equals to 0, we have to return 0, otherwise we return that particular value, right? Now let's look at these two functions. So this function is straightforward. We just have, let's say you have a value and you need to find out the index. So let's say you have minus 3 and you need to find out the index. So what is the index of minus 3? The index of the smallest element would be 0, right? So let's say the smallest element is s. So the index of s is 0. So and the index of s plus 1 is 1, s plus 2 is 2, and so on and so forth, right? So what you can do, you can simply subtract uh, like you can simply subtract x from the current value and you will get the index, right? So that's what we have done. We have simply subtract minus 50, or in other words, we just simply add plus 50 in the current value. Now why minus 50? Because minus 50 is the smallest value possible. Now because we are doing this in using segment trees, you can simply like have this exact same approach in the range minus 10 to the power 5 to plus 10 to the power 5 as well. In other, or in essence, you can also code it the same solution using minus 10 to the power 9 to plus 10 to the power 9 as well. But in that case, you have to just apply path like compression before doing this. So we can discuss that later. But for now, you can easily solve this exact same problem with exact same code in the range minus 10 to the power 5 to plus 10 to the power 5 as well, because the segment tree that we are building is 2 into the total values possible. So in this particular case, the segment, if the range is 10 to the power 5, the segment tree size would be 2 into 10 to the power 5, right? Now let's look at the segment tree function. So this is the standard thing. The update is standard, like we have to add this value to this particular index. So what we have done, we simply call this internal update function with 0 and minus 1 0. Now 0 and minus 1 represent the range, this particular range in the segment tree, right? And this 0 denotes the index in the array. So if you just to get you a quick recap, we are not storing segment tree using pointers. We are storing segment tree in an array. So the first node would be 0th node. Then the left child would be I cross 2 plus 1, right? And similarly, the right child would be I cross 2 plus 2. So that's how we are storing segment tree. So this node will come at 0th index. This node will come at first index, and so on and so forth. So what we are passing to our function is the range that this particular node denotes and the index of this node in this particular array. So the initial node is at index 0, and hence we are passing 0. Now in this particular thing, we once we reach the leaf, we know that we are at the node that we want to update. So we just simply increments its value to plus val. Now notice that we checked L to R and we incremented I because we know that this particular range is stored at this particular index I in the tree, and tree is nothing but an array, right? Now rest are simple stuff, like we decided whether to update the left half or the right half based on the index, and once we have done that, we just simply update the current node as well. So why? Because let's say you updated this to 3, so the sum of this particular node would also change. So that's what we are doing. We are changing the sum of everything that we have visited. So this part will do that. Now finally, the last function is first index greater than prefix sum x. wherein we want to find out the first index which have the prefix sum greater than equals to x. So we pass in x, and again this is standard path, the range 0 to n minus 1 and the index I. Here as well, if we reach the like leaf node, we need to check if the value is greater than equals to x. If it is, then we return the current index. If it is not the case, it means we have reached the leaf node, but still the prefix sum is not greater than equals to x. In other words, this can only happen if you reach this particular node, right? Let's say you know that the entire sum is 17, and let's say you have to find the first index where the sum is greater than equals to 18. So in that case, like when you do this searching part, you will be ending at this particular node with a value of, let's say, 5. So y5, we have discussed that, like as and when we are going right, we will subtract the contribution of the left half completely, because the right will not contain anything that the left half will denote, right? And as we have gone right, we are sure that everything in the left is already included. So that's why we'll just keep on subtracting the right half contribution. Finally, once we reach here, we'll get the value 5. We'll compare 4 with 5, and because 4 is less than 5, it means that will not get any index that has the value greater than, or that has the prefix sum that is greater than equals to 18, and hence we'll return n, or an index after this. So in this particular case, we'll return 8 from here, right? So this is what we will do when you reach the leaf. If you are not at the leaf, you will check the left half. If the left half value is greater than equals to x, it means what you are looking for lies in the left half. So we'll simply go to the left half with the same parameters. Otherwise, you will see in the right half. Now, as we have discussed, if we are going to the right half, it means we know that left half doesn't contain our answer, and we will be always including the left half in whatever result we will be getting after this, right? So let's say you get 4 as an answer. It means you know that you have already included 0, 1, 2, and 3, right? So because this is true, whenever you are going right, you will just subtract the contribution of the left half as well. So that's what we are doing. Because we are going right in this particular case, we subtract the contribution of left half and then go right, right? So finally, this will return the first index where the prefix sum is greater than equals to x. So hope this entire solution makes sense. If you have any doubts, feel free to post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. Now, coming to what's coming next, we will either be solving the next problem in this particular uh, topic, which is another lead code problem. Again, this problem can also be solved without segment trees, but we are solving this with segment tree to just strengthen our understanding of how binary search can be applied in segment trees. So you can try this problem by yourself. If you have, if multiple people are facing problem in solving this, I can upload a video there. Otherwise, we'll start with the merge sort tree in the next series. So stay tuned, and I will see you in the next one. Thank you.